In this video, we're going to be taking a look at electrical components. Specifically, we're going to look at switches, relays, solenoids, and different types of resistors. So first one, looking at the switch that's up at the top there, just a simple toggle switch, which is on or off. The contacts, you can see down the bottom corner there, contacts, that's a different types of switch, but inside there, as you flip the switch, it's just going to make the metal pieces come over and touch each other. So that toggle switch would be classified as a single pole, single throw, and it's a normally open switch. So you have to push on the switch, and it's only going to close on the one side. The image that I have down there at the bottom, that's a single pole double throw, and that type of switch really has no off position. It is on either way. The place where you'd find that on the car would be your dimmer switch, that it's on low beam to the one side, it's on high beam to the other side. Another type of switch that we have on the car, it's going to be a gang switch. And this gets a whole lot more complicated. So make sure that you're paying attention here. And first thing I want to draw your attention to is this dashed line that's going across here. This dashed line tells you that these switches, the four switches that you see there, are mechanically connected together. You can't move one without moving the other one, so they're all part of the same piece. The other thing about this switch is it shows you that it is a 6-position switch. Now this one's not really, it's a little bit deceiving. It's actually a 5-position switch. So this was on the older car when they had an accessory lock, off, run, and start position. So the ignition switch on your car is most likely a 4-position where you have the off, accessory, run, and start positions. So while you're looking at this image here, what I want you to specifically pay attention to is right now we're in the off position. You see there's no current flowing from anywhere. So up here at the top, this is going to be battery or hot at all times. If we turn this switch to accessory, keep in mind that all four switches are going to move to that same position altogether, but this switch right here is the only one that's going to do anything. So voltage is now going to flow down through here and go to radio, other things that would be on. It also ties into the run position. So the things that are on that particular circuit would be hot, both in the run position and in the accessory position. Now, as you get over here to this one, so this again is the run position, but this line right here tells you that this is hot in both the run and the start position. So that would be things like your engine computer, fuel pump, fuel injectors, O2 sensors, ignition system, everything that needs to be operating both while the engine is running and while the engine is cranking. So this one here is only going to be hot in the run position. And if you have something on your car that will only work if the key's on, well, it's going to feed off of that wire there. So this is a ganged switch. You see a second dashed line that outlines this whole switch. That dashed line tells you this is an incomplete picture. So the switch does more. So for example, they don't show us anything that happens here. And where they have this bulb test here, they also are not showing us this bulb test. So you'd actually have to go to a different wiring diagram to find out what those actually do. Next, taking a look at a relay. So I've opened up a relay so you can take a look at it up there at the top. This is what is referred to commonly in the industry as a Bosch style relay. It's also referred to as an ISO for Industry Standards Organization relay. It is a 5-pin relay, most of them. Every once in a while you'll find one that is a 4-pin relay. And up here at the top, this is your electromagnet. So just a single strand of wire that's wound around there probably about 1,000 times. Run current through there. It's going to build up a magnetic field. And this arm right here is going to get pulled down. So it's going to switch this from the top down to the bottom. Purpose for using a relay is to control a high current with a small current. And don't get that confused. A lot of people will say, and I think they're just mistakenly saying, a high voltage with a low voltage. They can wire up relays, like in a home application. But on the car, this is going to be controlling a high current flow with a small current flow. I guess with our hybrids now, we do have relays that using a 12 volts to control your high voltage on your traction battery. So looking at the 5 pins down here, we have this pin that's down at the bottom. This is pin 30. If you've done anything with European cars, you know 30 designates hot at all times. Now, on the top part of this box, they show you right here that pin 30 is connected to 37A. So where you see this is closed right here, this side of it up here is going to go to pin 30. This one goes to pin 87A. It's normally closed. So there's continuity between those two. This line right here, they drew it in as a solid line, but when you're looking at a wiring diagram, and we'll see that in a little bit, this is normally a dashed line, which tells you that this is controlling the switch, and this is your electromagnet. So I hope you're taking notes and getting it written down. So just put a heading on there for a dashed line. So a dashed line can mean incomplete. A dashed line can show you that everything is moving together or controlled together. And the dashed line can also show you that it is being controlled by something else. So this would be an example of a mechanical switch that's being controlled by the electromagnet. So when the relay is energized, we'll then have continuity between 30 and 87. I did that backwards. 30 is down at the bottom, 87 is at the top, and then it'll be open. So if you were to take an ohm meter, when the relay's off, you'd be able to measure continuity between 30 and 87A, but not between 30 and anything else. If you energize the relay, so our 86 is this one, 85 is this one, put power to one, ground to the other one. It doesn't matter which one is power, which one's ground. It'll then energize the relay, and then you'd be able to measure continuity between 30 and 87. Between pins 85 and 86, typical, you'll find about 70 to 90 ohms in there, which means our current is going to be about a quarter of an amp. We're going to be down in the milliamps. And on this relay, they actually lie to you. They tell you the normally open is good for 40 amps and the normally closed is good for 30 amps, which means 30 to 87 can handle 30 amps, 30 to 87A can handle 40 amps. But what I didn't show you is on the side of this relay, it says the normally open is good for 25 amps continuous. So it's not really as good as they're telling you. If you spend the money and buy a good one of these relays, typically they're good for about 25 amps on the normally closed and about 30 amps on the normally open. The reason the 30 to 87 is the higher amperage is because the electromagnet's pulling that down farther or harder. It's making better contact when it's down there. So you're going to find these relays all over the place. Everything coming out of Europe has used this style of relay. Most all the Japanese cars have used this type of relay. To my knowledge, Nissan is the only manufacturer that never used this type of relay, and that's because Nissan makes their own relays. Most all the domestic manufacturers have used this relay at one time or another. If you buy an accessory for your car, say driving lights or something like that, it'll come with a relay to wire it up, and it's going to be this style of relay. So this is a really good relay to get to know and get to understanding how it works. So looking at a drawing again, so here's your 30, 87, 85, and 86. And on this one here, when you see that style of drawing right there, that's a winding or it's an electromagnet. And what they've done is they've wired this resistor in parallel with it because EMI, when you shut this off, that electromagnetic field is going to collapse down immediately and you get a voltage spike. And that voltage spike can travel through and damage electronic components. So by having this resistor, when it gets the spike, the current will now flow through this resistor and right back into the electromagnet, protecting everything else. And here's the dashed line that I was showing you, that this switch is controlled by this electromagnet. So there's the three different meanings for a dashed line. And as we get into the wiring diagrams, we're going to find out that they have some more too. I hope that helps you understand these relays. So the manufacturers have now been going with a smaller, more compact relay, but it still does the same thing. And when you look at a relay and need to test it, you can check continuity across the control side of the relay. So I should point that out. This is the control side of the relay, the solenoid or the electromagnet. And then The 30 to 87A or 30 to 87 is the switched side of the relay. So anytime you're looking at a wiring diagram that has a relay, you have at least two separate circuits that you need to diagnose if it's not working correctly. The next one is a solenoid. Again, looking at the pattern over here, that's our coil that's wound around. And on a solenoid, electrically, that's all it is. It's just a wire that's wound around a whole bunch of times. And looking at this one here, you can see the scrape marks on there. And this is the plunger. This is the movable part of it. With a solenoid, we're going to use electricity to create mechanical movement. So we have solenoids all over the car. This is something you really need to understand how it's working. On this one, it has just a single wire coming into it. And that's because this housing here is the ground. So when they put power here, the electromagnet is going to energize, and this plunger is going to be drawn up inside of there. So this spring is what holds it out. The electromagnet overcomes the spring tension plus whatever this is connected up to make it move. I put a fuel injector over here on the left-hand side because a fuel injector is just a very expensive way to say solenoid. And I don't know why that switched on me. So we can control liquid movement, we can control air movement. So they have solenoids, again, all over the car. Now we get to this type of resistor. We'll go through this part fairly quick because although this is nice to understand and it's kind of fun, it's not something you're going to use very often. So if you don't follow along this part, it's not that big of a deal. Because besides that, if you do need to use it, there's a lot of different sources on the internet that'll help explain how this works. So a lot of times when you find the directions on it, they will tell you, okay, the first band is this, the second band is this, the third band is this. The reason that gets confusing is because you're going to find resistors that have 3 stripes on it, 4 stripes, and 5 stripes. And so it changes around. So the way that I'm going to explain it to you is start with the last stripe instead of the first one, which if you've never done this, you're looking at this, okay, how do you know which one is the last stripe? So I'm going to draw your attention down here in the bottom right corner. See our gold, silver, or none. The gold and the silver are only used on that last stripe. So most of the time you just look to see where the gold stripe is or where the silver stripe is, and that's the last one that you're going to use. So looking at this one over on the left-hand side, here's our gold stripe. So that's the last one. A gold stripe tells me that it's plus or minus 5%. So that's the tolerance. So when you see the gold stripe, that's a pretty good resistor. My second to last stripe is going to be my multiplier. So this center area here is my multiplier, which is going to be anywhere from times 1 to times 100 million. So extremely high resistances when you get a gray one there. But this one is black, so it means we're going to multiply by 1. And on this one, because we have 4 stripes, these first 2 stripes are going to be numbers. So looking at the first one, it's orange, which orange is the number 3. Second one is brown, which is the number 1. So that's going to give me the number 31 there, times 1. So that's what we're looking at down here. 31 times 1 is our 31. And then our tolerance, plus or minus 5%. So if you're testing this resistor, if you want to know it's good or bad, its resistance should be greater than 29.45, less than 32.5. If it's higher or lower than that, it's bad. It needs to be replaced. Now, looking at the 2 resistors that are in here, this one has 4 bands on it, just like the one we were looking at. But when I look at this one, it's like, is that orange or is that red? So if it was orange, that would mean it's 3. If it's red, then that means it's 2. And sometimes when you're dealing with these little resistors, especially when you get the really tiny ones, it's hard to be able to tell what color that is. I've had multiple discussions with students as we're looking at them as to what color that actually is. And sometimes I measure the resistance and then figure out what color it's supposed to be depending on the resistance that I got. This one here is there 5. And again, it's hard to tell the colors on there. So this last one is brown, and the reason I know that is because they're telling me it's plus or minus 1%. And so when I'm looking at my tolerance, the brown is 1%. Physical size of these resistors is going to determine the wattage that it can handle. You're going to take your voltage times the amount of current that you would have on the circuit to figure out how many watts, and then make sure that you get one that can handle that much wattage or more. Ideally, you want to go with more, because otherwise you'll end up burning it up. Now on here, if you're using a calculator that doesn't have the percentage button on there for you, here's your math. So finding my pointer there. On this one I'm using a 50 ohm, and I just made this up, and a 5%. So 50 times 0.95 is 47.5. 50 times 1.05 gives me a high end of 52.5. So 0.95 or 1.05 is going to give your plus and your minus tolerances. If you have a silver stripe, which is 10%, which most of these resistors that I see have one of those two colors, it would be 50 times 0.9 or 50 times 1.1 to give you your low and your high tolerance on there. So this one here, we have the silver stripe up at the top. So it's 10% tolerance. A black multiplier, so times 1, and then 2 red stripes. So I've got 22 times 1, which is going to give me a 22 ohm resistor, plus or minus 10%. So 22 times 0.9 gave me 19.8. 22 times 1.1 gave me 22.4. So when I go to test the resistor, I want to make sure that it's within those numbers. Otherwise, replace it. So this one here is a 5 stripe. This one is a really high quality one, so it's got that brown at the very end. And then silver is my multiplier, and this silver tells me it's times 0.01. So 3 stripes. Starting at the bottom is the brown, which is a 1, the green, which is 5, and the black, which is 0. So I've got 150 times 0.01. So this resistor should be a 1.5 ohm resistor. And then with a 1% tolerance, took it the 1.5 times 0.99, which gave me my 1.485, and 1.5 times 1.01, which gave me my 1.515. So hopefully that helps you with understanding these resistors, what the stripes mean, and how to use those stripes to figure out what the value should be. One of our first types of variable resistors that we're going to look at is going to be a stepped resistor. So looking in the bottom left-hand side, that's typically what it'll look like. This is a blower motor resistor, and those resistors are going to build up a lot of heat, so it's always going to be located somewhere close to the blower motor, so the air from the blower motor is going to blow across those. The wiring diagram over here, there's our 3 resistors. So power coming from here, turn the key to the run position, we're going to have power coming to our blower motor, and then from ground it's going to come down, and depending on what position this switch is in. So if this switch is in the low position, current has to flow through all 3 resistors and then to ground. Each time the current flows through a resistor, it's going to drop the voltage. So we're dropping the voltage to the blower motor, meaning the blower motor is going to run slower. If you turn this switch to the medium low position, current's now going to flow through just 2 of the resistors, and blower motor will spin a little bit faster. When you get to the medium 2 position, goes through just 1 resistor, and then in the high position bypasses the resistors. So on a lot of the newer ones, they have a thermal fuse in here, so that if something goes wrong and these get too hot, it's going to pop the circuit open, and your blower motor will only work on high. Second type of resistor, and this is a rheostat, and new cars have gone away from using the rheostat. A rheostat's going to be identified by 2 wires. So if you look at this image here, you can see we have just the 2 wires connected up to it. So looking over here at the wiring diagram, you see we have a resistor, and on the early ones, this was a small wire that was wrapped around an insulator. Later ones, they went to a resistive strip, and there's a sliding contact that moves across back and forth on that. On this circuit, it goes to ground. So if it's over here, it's going to be high resistance, If it's over here, it's going to be a very low resistance. Again, we're going to change the amount of current flow, and this is, as you can tell, is the fuel gauge, and how much current flows through here is going to tell you how much fuel is in the tank. So here's our float. It's going to move this arm up and down right here across that resistive strip, and it's going to control the current flow through there. So that's a rheostat, 2 wires. Potentiometer, this is what you're going to be dealing with, so make sure that you understand this one. We have the same thing. We have this resistive strip across here. There is a sliding contact that's going to move across there, but instead of using battery voltage, you're almost always going to find this 5 volts being applied to it. So it's coming from the computer. It's going to be a purified 5-volt signal, so it doesn't matter. Battery voltage at 9 volts, battery voltage at 17 volts. This will stay at 5 volts. And then this side here, we're going to ground, and that is an engineer's ground symbol. So by having 0 volts at the bottom here, 5 volts at the top, as this thing slides across here, we're going to vary the voltage. So typical range on a potentiometer, which if you're talking with somebody that's dealing with electronics, they're not going to take the time to say potentiometer. They will just refer to it as a pot. So highest voltage you'll typically see is about 4.5 volts. Lowest voltage you'll typically see is about 0.5 volt. And it can monitor the movement across there. This one, the image that I'm showing you here, is a throttle position sensor, and the diagram is for a throttle position sensor. So they started putting computers on cars in the mid-70s. By 84, everything had a computer for the engine. And so from 84 on, I don't think you can find a car that was sold or made for sale in the U.S. that does not have a potentiometer. When we went to our drive-by-wire systems, we now on the throttle will have 2 or 3 potentiometers. On the accelerator pedal, they'll have 2 or 3 potentiometers. There are other potentiometers located on the car. The fuel gauge now, to read more accurately, they've gone to a potentiometer instead of the rheostat. So if you're going to be working in this industry, you're going to be working with potentiometers. It's really good to understand this. If you want to test the potentiometer, ideally, just leave it on there and back probe this signal wire right here. So voltmeter to ground, your black lead to ground, and the red lead right there, and then move the potentiometer through its full range. Watch your voltage as it changes. You should see a smooth voltage change as it moves across there. If you see the voltage jump, there's a bad spot on the potentiometer and needs to be replaced. So this is used in electronics, but this is really not an electronic component. It has a mechanical movement in there. It is a contact that slides back and forth across that resistive strip, and they do go back. So that's the end of this video. I hope that was helpful for you, and I will see you on the next one.